Good morning, everyone. So we're doing exponential and logarithmic functions as our next topic, and I did actually want to look at the aims, the objectives, whatever you want to call them for this. So reading through to graph exponential and log functions, which you should have a pretty good idea already, to introduce Euler's number, which is E. So when we actually have used E before, I don't think we've ever talked about it as Euler's number. So that's actually what it is, and we'll define that a little bit later. You will need a lot of your index and log laws that you've previously used. We're going to solve some exponential and log equations, and then we'll find the rules from the graphs. So hopefully we're getting pretty good at all this. And because we can now do inverses, we'll do the inverses of exponentials and logs, and then apply these to modelling and growth problems. So that's our sort of aims. So we'll have a look and see what we've got from here. A lot of the concepts you've used previously in all your topics will be used here. So it should be, a nice easy week for you as far as easy weeks go. Okay, so an exponential function has the rule f of x equals k by a to the x. So you can have lots of bases. It doesn't have to be e, it can be 10, it can be 7, it can be whatever number we want that a to be. So where k is a non-zero constant and the base a is a positive real number other than 1. So it does have to be positive. It can be less than 1, but it's still got to be positive. Exponential functions you would have done in last year in Math Methods Units 1 and 2, and they actually come up in many practical situations, and we'll look at a couple of applications sort of towards the end of it. We're also going to introduce Euler's number, which has many interesting properties. The most interesting is probably that the y value, so f of x, is always equal to the derivative. And we know that from the rules we've done with differentiation already. But we can actually define Euler's number as the limit as n approaches infinity of 1 plus 1 on n to the n. And again, we'll look at that in more details, probably in about exercise B, I think. So let's get on and sort of actually start the work. Exponential functions. Now, not assuming anything, so that's sort of one of the reasons I'm doing this video. The function f of x equals a to the x, for a is an element of real pluses excluding 1, is an exponential function. The shape of the graph depends on whether a is greater than 1 or whether a is between 0 and 1. So you can see from the example below here, when a is greater than 1, that's our typical sort of graph we've got. Looks like this. A couple of points you should sort of always put on. If it's a to the x, so if at x is 1, a to the 1 is just a, so you get that point 1a. All of these graphs have a y-intercept of 1, so when x is 0, anything a to the 0, anything to the 0 is 1. And if you chose the point -1, well, a to the -1, well, -1 in the index just means 1 on a, so you get that point -1, 1 on a. And the alternative is when a is between 0 and 1. So when a is between 0 and 1, think of about what you have. You've got, if a is between, is between 0 and 1, then let's say that a was a half. So just say if a was a half. So then we would have a half to the power of x. And a half can be written as 2 to the -1 to the x. So then it's 2 to the minus x. And remember, when the minus is in front of the x, it's just a reflection in the y-axis. So if you took our graph that was on there where for a greater than 1, do a reflection in the y-axis, clearly you get this graph here. And notice that is an asymptote along the x-axis there. So at y equals 0. Okay, so key values, f of -1 is 1 on a, f of 0 is 1, and f of 1 is a. the maximum domain is reals, and the range is, doing the range of the y values, so real positives, doesn't count 0. And the x-axis is a horizontal asymptote. Okay. An exponential function with a is greater than 1 is strictly increasing. So in other words, all points, if the further right you go, the point of where I am at the moment, any point to the right of that will be higher than the previous point, which is what strictly increasing is. And for a is between 0 and 1, it's strictly decreasing. So clearly it's got a negative gradient there. Any point to the right is lower than the previous point. Its y value is less than the previous point. Now, we'll use our transformations and things that we've done before. So graphing f of x equals a to the x. So if the translation xy is x plus h, so moving h units to the right or in the positive direction of the x-axis, and k units up, so or in the positive direction of the y-axis, is applied to the graph, then the image has the equation a of x minus h plus k. The horizontal asymptote of the image has the equation y equals k, so just that little bit there. And the range of the image is k to infinity. So let's just sketch one little graph here. So I'll see if I can grab myself an axis here. Sketch the graph and state the range of y equals 2 to the x minus 1 plus 2. So draw in a nice axis there. That should be good enough. And I will click away, he said. There we go. And just rub that line out. So sketch the graph y equals 2 to the x minus 1 plus 2. So if I sketch in my normal just 2 to the x. There we go. Very smooth this morning. Y equals 2 to the x. Hopefully that's made Lucy smile. Right, 0, 1. And of course, because I always like to put the arrows on y and x. Now, if I want to sketch the graph of this one, what have I got here? I've got a translation of 1 unit right. I won't write out the whole wording. Translation 1 unit right. So let's draw that in, and I think because I've actually got a mouse here when I'm working at home, so if I click on that, I should be able to copy that and then paste it. Oh, look at that, how good's that? And so I can put it on, and now I can translate that 1 unit right. There we go. So that's 1 unit right. Okay. Probably could change the color if I knew how, but that's okay, I won't. And if I paste that again, so I've gone 1 unit right, and now if I paste that again, I should be able to then move that up. How far are we moving up? 2 units. So I've said that's 1, so obviously that's got to go up to 3, moving that up vertically. So about there. I think what I might do is just go over that in a different color pen to make that a bit clearer. So I'll go over that in blue. That's a real test. It's a bad color to go over it. Maybe I'll go over it in black. Need a thicker pen. All right, there we go. So now we've got, because we've translated up, we've got a y-axis and y-asymptote. So that y-asymptote was moved up 2. So that's y equals 2, the new asymptote. This point here that was at 0, 1 went across 1 unit and up 2 units. So that point there now, instead of being 0, 1, across 1 unit made it 1, up 2 made it 3. And you would need to work out the y-intercept again. So if we want the y-intercept x equals 0. So we have what? Y equals 2 to the negative 1, because x is 0, plus 2. 2 to the negative 1 is a half, so that's 2.5, so that's 5 on 2. So this point here is 5 on 2. So 0, 5 on 2. And that should be all we would need. We've got 2 points marked in, so we've now got it defined. And that's its little graph, which is lovely. All right, move on. Now, an interesting little note here, and this, I'm expecting this to come into an exam. I haven't seen it for a little while, but I'm expecting something like this in an exam, and certainly worth noting. Right, since the graph 9 to the x on 2 is actually 9 to the half times x, well, 9 to the half square root of 9 is 3, so that's 3 to the x. So the graph y equals 9 to the x on 2 is the same as the graph y equals 3 to the x. Similarly, the graph of y equals 3 to the 2x is the same as 9 to the x. 3 squared is 9. So just using your index laws. But it's more this part here that's the more interesting bit. And translation parallel to the x-axis results in a dilation from the x-axis. So how can a translation actually be a dilation? For example, if the graph y equals 5 to the x is translated 3 units in the positive direction of the x-axis, then the image of the graph is the graph y equals 5 to the x minus 3, which can be written as 5 to the negative 3 times 5 to the x. Hence, the translation of 3 units in the positive direction of the x-axis is equivalent to a dilation of factor 5 to the minus 3, which is 1 on 125 from the x-axis. So I'll try and show that just a little bit better than that.